Today we're going to learn about the Brittle Coulomb-Mohr Theory. Now this is very similar to the ductile Coulomb-Mohr Theory. The only difference is that in ductile Coulomb-Mohr, we're concerned with the yielding surface when a body starts to plastically deform. And in the Brittle Coulomb-Mohr Theory, we're worried about the ultimate tensile strength when a body is going to fracture, when it's going to fail. So, the Brittle Coulomb-Mohr Theory, what is it? It's that fracture can be determined by taking the results of fracture tests in tension, compression, and torsional shear stress, and using them to plot three more circles that define the failure envelope, right? So we conduct three different tests to fracture or to failure of our geometry and create more circle to figure out the state of stress where failure occurred. Now, the mathematical form of the Brittle Coulomb-Mohr theory is very similar to the ductile theory, where the first principal stress divided by the ultimate tensile strength minus the third principal stress divided by the ultimate compressive strength. If it is greater than or equal to 1, then fracture or failure of our structure occurs. Now, taking this equation, since it is a linear equation, we can evaluate three different cases and form our failure surface for Brittle Coulomb-Mohr. Case 1, let's assume that the first principal stress is larger than the second, and the second is larger than 0. In that case, sigma A is equal to SUT over N, where N is our safety factor. Case 2, if sigma A is greater than 0 and 0 is greater than sigma B, then we get our classic form of the equation. And on the right-hand side, we'll say 1 over N, again, where N is our safety factor. And then case 3, if both of the stresses are less than 0, then we get the case where sigma B is equal to negative SUC, so our compressive tensile strength, divided by our safety factor. With these three cases, they each create three lines, line 1, 2, and 3. And through symmetry, we can then define our other three lines in order to enclose a failure surface, where if we are inside of this surface, our design is safe and it has not failed. But if our state of stress is on or beyond this surface, then failure will occur in our structure. Now, what happens when we plot the Brittle Coulomb-Mohr theory with real data? Well, let's take a look at it. We can see that, at least in this initial quadrant, it's right in line with the data. But as we move into the fourth quadrant, when compared to the data, which are the dots, it is fairly conservative in this quadrant. Conservative meaning it predicts failure sooner than it would actually occur in real life, right? So it's kind of defining an envelope of stress as, oh, we think it's going to fail, but in reality, there's a little bit more stress that our structure could support. So this theory, Brittle Coulomb-Mohr, is conservative in the fourth quadrant, so it underpredicts the stress at failure. And even though it is conservative, conservatism isn't a bad thing. Conservatism means that we have an additional design safety factor built into our design if we use this equation. So Brittle Coulomb-Mohr is very good when we have a design where we need a little bit of more cushion on our safety factors.